Hello everyone, this is Jeff Z. Today I'm going to share my learning experience of LeetCode problem 110 balanced binary tree. It's an easy problem, so let's jump into the description. Given the binary tree, determine if it is height balanced. Uh, so so for this problem, a height balanced tree, a binary tree, is defined as a binary tree in which the left and the right subtrees of every node, so this is important, every node differ in height by no more than one. Um, there's some examples. If you see this tree, no matter in which level, the the height of the binary tree, subtrees, are within one. So in this case, on this node 3, the left height is actually the left subtree. The height is 1, and the right height subtree the height is 2. And on the node 9, there's no left to right, so basically true. And on the right node 20, it has the left node and the right node is 1, left subtree the height is 1, right subtree the height is also 1, so it's true. Example 2, so here okay, this is split by the page. So if you see the tree, you have the left, which is 1, 2, 3. You have 3. The height is 3, the left subtree. And the right subtree is actually 1. The height is 1. So it's definitely larger than 2. The difference between left and the right subtree, the height is actually, sorry, the height of the difference of the height is actually more than 1. So it's returned false. Okay, so let's jump into the solution one. So the solution is you'll always get the left and the right tree. This is kind of a brute force recursive solution. Um, you'll always get the left and get the height for the left and the right subtree. Sorry, it has subtree. Then compare, do the same for the left and the right. Do the same for the left and right children. This is what I mean. Um, you need to pay attention again that you need to from the problem you need to pay attention to that the concept of the balanced binary tree is on every node the differ in height. The left and the right subtree, the differ of the height should be within one. And also, in the code, you need to make sure you check this on itself and also on its children as well. So I will show you what I mean here. So this is actually the main function. Uh, the input is the root node of the tree. You have the root node. If the root node, you need to check the root node. If the new root node is null, return true, which means that I assume this is like if there's no node, I assume that it's balanced. Again, depends on you need to ask a question to interviewer to confirm this if it's gonna be true or false if the root node is no. Then you need to get I actually create a helper function called get height to get the height of the subtree. So in this case, I have the left. I have the get height root dot left to get the left height and get the right height, and then I will make sure that the left and the right height, they are they are smaller than 1. sorry, the absolute value between the left and right should be smaller than 1. And then I also need to check if the the left child and the right child are also the same situation. And okay, this is the get height function. What you see is you have the node, and also you have the level. This is basically the level that you need to remember. Okay, you are at certain your how what sorry how deep the binary tree is. It can named as height. It's the same concept. So if node is no, that means it's already done. You just directly return it's already past the leaf node. Then you pretty much return the level. Otherwise, you will basically say, okay, I wanted to go one level deeper, which gonna be the incremental level, same as the right side. Um, then then you need to actually compare the left side and the right side to see which one is larger, because you always need to return the larger basically the larger height, which gonna determine the height of the subtree. In this case, let's say if we have this tree, this is if we have this subtree, assume that there's let's say if there's child node, let's say if there's a no uh, the right child node doesn't exist, and then in this case it has still we need to consider this as the height is 3, because it has the left child node, which from here 2 to 3 to 4 it's actually the height is 3. That's why we need to use the max to get the height. So this is a brute force solution, and the time complexity is actually O(n) square. So what happened is for every level, every node, we need to actually it's an O(n) to get the height. But the problem is we need to also get you know we need to traverse another time, basically have when on the left child node and the right child node. That's why it's O(n) square. Um, yeah. So the space complexity. So the space complexity is actually O(1), because I don't think we yeah, so I don't think we introduce any additional space. Just a second. Let me double check. Okay. Okay. Um, all right. So all right. So it didn't mention about brute force solution in this in the discussion. Um, but yeah, but I believe this is O in sorry the space complexity is O(1). Um, all right, so the solution 2 is using a slightly different way. Is you don't have to you don't have to yeah, slight different way is you don't have to kind of traverse all the way, check every node. The reason is it's using -1 to represent uh, if it's not balanced at a certain level. Um, in this case, it's basically traverse, so you don't have to maintain the level in this case. So what happened is you pass in this node. you say, okay, if it's the node is null, which means it's on the leaf node, it returns 0, then you basically need to check the leaf node, the node dot left, and the left height. Uh, so the -1, the -1, has a special meaning, which I will show you next. So uh, that's why it specifically check if the left height is -1 or not. If it's already -1, you don't have to check the right height anymore because it's already unbalanced. Um, and if assume that the left and the right is not unbalanced, then it will actually go here. So this is where it's actually return -1 is. It will check if the left and the right height. uh, Assume that you are already on the child node, which means that it will say the child node to return 0. So in this case, 0 should be fine. Then the child node will return. Yeah, it will get to the max right and sorry max of the left and the right plus 1, which is going to be 1, and then it's going here. It will say, assume that the left and the right, they are all 1, so it will say, okay, um, is the left height minus right height, the absolute value is larger than 1, which means that it's at the bottom. Let's say uh, it will say like, as at this moment, at this level, is it already unbalanced or not? Is at this level, is it already unbalanced or not? Or at this level is already unbalanced or not? So if it's already balanced on the lower level, it's a bottom up solution. So if on the lower level it's already unbalanced, then it will directly return -1, which is going to be here. Sorry, which is going to be here, and then it will actually check, okay, if the left is already -1, it will return all the way to the upper level, and then all the way to the root. Then you can skip the other side of the check. And yeah, so if it's still within 1, the left and the right still within 1, then you basically just, the similar idea is you need to get the max of the left and the right and the +1, which return the actual height. In this case, the time complexity is O(n), because you only check once. There's no um, kind of you don't have to double check, okay, is the left or the right is also balanced or not. It's kind of a waste of waste of the time. That's why this solution is time saving. And the space complexity, I think it's O(1), because it's just a traverse, I assume. So this is what let me see, sort process, sorry, hit the wrong button. Sort process. If the left or the right height is -1, then it needs to intercept the subsequent logic. So this is what I said, and it's cascading applied to the upper level all the way to the root. If the height of the root is -1, that means the entire tree is not balanced, right? So it will basically return that, false. We need to check if it's the height, if we get the height of the root, if it's equals to -1 or not. Okay, so this is the two solutions of solving the balanced binary tree. Um, And this is just my learning experience. If there's anything that I said is not clear, or it's causing confusing, or some problem, just let me know, and I can I can record the video one more time to correct all these problems. Thanks for watching. See you next time.